Hi. Can hear? Testing. Let me try. Hello. Good afternoon. See whether I can hear. Yes. Can hear? Can hear? Can hear? Yes. I think you all can hear me. Let us wait for another 1 minute. I will start today's lecture. So today I will cover about the topic of this week, the analysis of algorithm. Good. Yeah. Same things. So today I will talk about the one of the important concept in the analysis of algorithm, the time complexity, the space complexity, and order of growth and asymptotic notation, how to represent the order of growth, and then use the order of growth to represent the time complexity and space complexity of an algorithm. So that is what we are going to cover in today's lecture. Okay, now it's 3:30. Start the today lecture. So this part again, I have mentioned on Monday. It's not surprising that there's no any coding involved in this portion. It's mainly analyze the algorithm, the complexity of the algorithm. So it's a lot of mathematics involved here. There's no coding involved, but we will test you in the final quiz. Of course, not only this in the final quiz, but you expect this part will be covered, will assess you during in the final quiz. Yeah, the lab test we won't be able to test you this kind of thing in the programming question. So analysis of algorithm, basically why you need to learn this analysis of algorithm is because there are a lot of solutions to solve a problem, but different solution we need to judge, we evaluate the speed and the scalability. That means if the problem input size grow, how does this algorithm will be affected? Yeah, the efficiency, how the efficiency change as the input size grow. I mean, it's not only simply increase the input size by 1 or by 2. It's like if I increase the input size 10 times, 100 times, 1,000 times, million times, how does the algorithm efficiency affected? Yeah, that is something we want to know before we implement such algorithm. So also we want to use the analysis of algorithm to identify the most efficient algorithm for a given problem. And also we also would like to understand the trade-off, because I will talk about the time complexity today mainly. When there's another issue is the space complexity. Time complexity is more about the times you take to run that algorithm. Then the space complexity is about the space, the storage, the memory you use for solving that particular problem. So sometimes there's a trade-off between different approach. Some maybe need to use more times, some may use more memory to solve the problem. And sometimes it's not the most efficient algorithm. Sometimes the problem is like you have limited resource. Maybe you want to you implement your algorithm on a device which have limited memory. In such a case, you may not be able to use the algorithm which need to use a large space complexity, and then you will choose the one using lesser memory. But sometimes you want to achieve your algorithm as fast as you can. That's most of the time the situation. Then in such a case, you will choose the one with the lowest order of growth. The lowest order of growth time complexity to solve the problem. You will choose that approach. So it's like depend your resource also to decide the algorithm you want to choose to implement to solve particular problem. So in short, we will discuss two complexity, time complexity and space complexity. I mainly focus on the time complexity because once you know how to analyze the time complexity, space complexity is you can use a similar way to evaluate, to measure the amount of memory unit you use by an algorithm. Then time complexity is the amount of time used by an algorithm. And how do we measure the amount of time? So actually, they are not really run the program to test how long you take, because by doing that is unfair, because different computer have different computational power. So if you use a supercomputer, of course, it should be run much faster than your home or your laptop computer. So that is not the right a fair approach to measure the time complexity. What they actually do they are trying to count the number of primitive operation in the algorithm. So what are the primitive operation? It can be you make some declaration, you declare some variable. Yeah, it will cost some time to create that variable. So that one will take time. So we need to know how many such as operation you did in the algorithm. It can be assignment. You assign a number to certain variable. That also costs you some time. So we need to know how many assignment operation you did in the algorithm. Of course, not surprising, the most common operation you need to use by using the computer to solve the problem, you definitely need to use the arithmetic operation, addition, subtraction, multiplication, division, modulation, logic operation, all the logic. When you use the if-else statement, definitely there's or while loop, you definitely have a lot of this kind of condition statement. So whether it's equal, not equal, greater, lesser, and or not, and so on and so forth. All this is a kind of a primitive operation. You will take sometimes, but all this operation itself, if it's only one operation, the time you take, you can think that it's a constant time. It takes some constant time. How long is 1 microsecond, 1 nanosecond is a constant time. To declare a variable, it takes a constant time. You use supercomputer, you use the normal computer, it's just like a certain period. Yeah, you take certain period to run such operation. Yeah, one operation is not an issue. The problem is like you run this operation many times. Then that will cost you some times to complete. And that is always and itself is not related. Here what I mean that they are not related is like itself is not related, but when you're trying to repeatedly run this thing, like I create a for loop to repeatedly do particular operation, that for loop is the problem. It related to the problem size. If my problem size is increased, maybe I need to run more iteration. Imagine my problem size, if it's n equal to 10, I run 10 iteration. If the n equal to 100, I increase the problem size from 10 to 100. Let's say I increase 10 times, which implied that such a operation, such a while loop, I need to repeat particular primitive operation 100 times. I increase 10 times. I increase to 1000, then you need to run 1000 times. And that is something we are interested to know. That is what the so-called the computational times we want to analyze. That's a time complexity we do to in the next few slides we are going to discuss. Itself is not an issue. If it's declared one variable, well, it's a constant time. You tell me that your computer is very, very slow, it's still a constant time. It takes 1 microsecond, 1 millisecond to declare a variable. But that is always 1 millisecond for one operation. But the problem is like when you run such an operation in a while loop 10 times, 100 times, it depends on the problem size. The problem size increase, then this particular operation, the number of operation you need to execute will increase significantly, depend on the problem size you have. So when we analyze the time complexity in any programming language, okay, this one nothing related to programming language, but all the algorithms normally have three kind of structure we need to analyze. One is the repetition structure, for loop, while loop, do while loop, or selection structure. If L switch case, we need to discuss. We need to talk about it when we analyze the time complexity of an algorithm. Another one is the most difficult one, I think is the last one, recursive function. If the function you have, the algorithm you have is a recursive version, is a recursive algorithm, then the time complexity is, as I said, the definition is the number of primitive operation. The number of primitive operation of all the function call you did in the recursive function. Yeah, we need to find out. So let us see the easiest one first, the repetition structure. So normally they will express the time complexity in terms of the problem size because it's related to the problem size. And like I mentioned in the first slide, that is we want to consider the scalability. If I increase my problem size 10 times, 100 times, 1000 times, how does it affect the performance of that algorithm? Yeah, that is the time complexity we want to do. So give you an example. This is an algorithm to calculate the factorial of n. So this depends on the n. Okay, let me quickly go through. First, you need an variable to help you. I declare a j. Then the factorial, I declare another variable called factorial. And then initially I let it become 1. All these first two lines, I may need to take some constant time to assign 1 to j, assign 1 to factorial. Moreover, I need to declare a variable j. I need to, of course, here I didn't include. I need to declare the variable and so on and so forth. Depend the programming language you use. That is not important because no matter how such an operation, all these operations take some constant time only. Maybe C0, maybe C1. The key is the next line, the while loop. You check the condition, it actually also costs something. J less than or equal to n. That also costs you sometimes. But again, that is a constant time, not critical. Then in this while loop, I did two things. One is I trying to the factorial variable will multiply j, the current j value, and then update the factorial. That's one thing I do. Another one I did is I increase the j, increase by 1 in every iteration. So C2 and C3 need to run a few iterations, depend the problem size n. So that is the key. I need to run n iteration. If my n increase 10 times, my problem size increase 10 times, this particular algorithm will increase roughly 10 times. Plus that C0 and C1 is nothing one. It's negligible. If your n increase 100 times, 1000 times, C0 and C1 is a very small amount of time you compare to the while loop part. So overall, the time you need to take in this particular repetition structure algorithm is the C0 plus C1 plus all this constant. You declare the variable, you assign 1, you do whatever assignment operation in the first before you start the while loop plus the n iteration C2 C3, even you want to consider more, actually this part the condition is also take some time. Every iteration you need to check the j whether is less than or equal to n or not. Maybe got C4, doesn't matter. The key is this n. You will find that the time complexity, the times you need to take for this particular algorithm is a linear function of your problem with your problem size. The time complexity will increase linearly with the problem size. If you increase your problem size by 10 times, then the computational times will roughly also increase about 10 times. Plus that little constant time is negligible because you will consider the n can be increased to 1,000 million times. In that scenario, this C0 and C1, you will later in the later slide we will concern about this is linear or not, and this constant we will simply ignore. Later I will show you why is it so further. Another example, I can instead of one for loop I can make two for loop. It's a nested for loop, so that will be even worse. You will find that if I only do this particular primitive operation, I just sum out all the element in a 2D matrix and add into the sum variable. In this particular simple example, okay, in each iteration I only take constant time to complete. Let's say C1, but I need to repeatedly do this operation n iteration for each row, and then I need to repeat this procedure for each column n iteration. It's like m times n times C1 in total. So let's say if it's a square metric, is m equal to n. In that case, actually this is the function of, so which mean where is it? Let me find a pen. That means this particular function, you expect that the time complexity of this particular function actually is the n something c times n squared plus whatever constant, doesn't matter. Yeah, you maybe need to declare the variable sum, you need to declare the 2D variable whatever at the beginning, but it's okay. Overall, the key is the n squared, because when my problem size, this array I increase 10 times, the n increase 10 times, the number of row, number of column, each of them I increase 10 times, then this one will increase 100 times. If I increase million, then the number will be very scary compared to the previous algorithm. Yeah, so this one you will find that the computational times will quadratically increase with your problem size. Yeah, that's why here I put that. Yeah, actually I basically already ignore those constant time operation. The key I concern is the number of iteration. The more iteration I run, depend on the problem size, then the cost will increase, the computational cost will increase quadratically in this particular algorithm. So that is one problem. Another issue, you have whatever algorithm, you definitely have some if-else statement in your algorithm. Yeah, sometimes you may do this portion. Sometimes maybe you will run this part. In certain condition, you may run this portion. Certain condition, you may run another condition, another few different operation. So in this kind of a selection structure, then the time complexity, how we analyze the time complexity, you'll find that there are it's not simply count the number of primitive operation. There are a few possible scenario. Yeah, because you not always run particular primitive operation. So in that case, we need to consider, when we analyze this kind of algorithm, we need to consider a few things: the best case, the best scenario, and the worst scenario, and the average scenario. because so that people have a better picture how how is the time complexity of your algorithm in the best case and in the worst case on overall all the scenario, yeah, based on their probability, then the average case how the complexity it is, yeah, so that they can decide, because you may not always in the best case scenario, or you may not be always in the worst case scenario. So we also would like to know how average. And best case is normally not the things we concern. Average and the worst is the one. Because worst case we need to consider is like in the worst, a lot of times, especially we will implement in the real-time system. When you implement in the real-time system, of course you need to consider that in the worst case scenario, can you achieve in real time? But yeah, and then you also consider that in general most of the time, how is it overall, how is the performance, so that you can decide what kind of a resource do you need, which algorithm is the better algorithm. Yeah, so that is the things, right? For example, this example, when x is less than a, I will execute one operation. Else, when x is greater or equal to a, I will run two operations. Let's say that each operation take about the same times to execute, although it may not be true. But in this example, let me make this assumption. In such a case, my best case probably is when x is less than a. I only run one operation. So let's say C1. Then in the worst case, of course, you will execute is this part. Yeah, let's say I take more times than C2. Let's say this is my assumption. I assume that C2 is greater than C1. Okay, this simple example. So overall, if it's I want to consider the average, what does it average case means? Means that I need to consider the probability when x is less than a. What is the probability when x is less than a times C1 plus the probability x greater or equal to a. In that case, yeah, then times C2. Then that is the overall the time complexity. But for this particular example, not surprising, no matter you time, like I said, C1 or C2, all are constant time. Overall, is still constant time. So yeah, that is the probability. So overall, the time complexity of the selection structure, we need to consider when you see that your algorithm, there's an if-else statement, very likely that you need to consider the best case, worst case, and average case. So another example can be switch case. In this particular example, let's say I got 4 cases in my switch case. The first one, I'm trying to compute the summation. I'm trying to sum n number. Then the second one, which you just learned last week, I guess, the searching some item in the binary search tree. And then the third one, I'm trying to print out the binary search tree. In fact, all kind of a tree. Yeah, if you want to print out, it doesn't matter whether it's a binary search tree or binary tree. You have to print out all the nodes for me. Then the last one is trying to find some minimum. Let's say that the first one sum all the number, you need to take linear times. Then searching in the binary search tree is the logarithmic. And then the print out the tree. That's when you need to print out all the nodes. You take linear times. Then the last one is the searching the minimum. Let's say searching the minimum nodes in a binary search tree. Probably this one, yeah, you just need to take the logarithmic times to complete it. Example, yeah, just an example. So in this particular algorithm, yeah, which one is the best case among these 4 cases? Which is the best scenario? Which one is you take shortest time to complete? What do you think? The first one take 5n, the second one take 5 log 2n, the third one take 3n, then the last one take 4 log 2n. 1, 2, 3, 4. Case 3, case 4. Case 3 is this is 3n. What do you think? 3n is faster or 4 log 2n is faster? So 4, yes. So you'll find that actually log 2n logarithmic is much more faster. You just simply substitute some number n, you will know. N equal to maybe power of 2, let's say n equal to 1040, 1024. 1024 is 2 power to n, 2 power to 10. Yeah, if your n is equal to 1024, so this one will take 1000. Need to somehow run 1000 iteration, 1000 operation, whatever unit you name it. Yeah, it need to take in 1000. But log 2n, yeah, is 2 power to 10. That's means it's only 10 only. You just need to run 10 steps. You already finished the task. So not surprising that the logarithmic one definitely will be much faster than the linear one. So worst case, of course, is this 5n in this particular example. Then on average case, then I need to know the probability for each cases. Then I just simply sum it up. The probability times the time complexity for each cases times the probability, and then sum it up. Then that is the average case, the time complexity of average case of this particular algorithm. Yeah, here, as I said, yeah, of course, at the beginning, I need to have declared some variable, this and that takes some constant time. So here, I just simply said there's some additional constant time. That is not important. When your time complexity is a linear function, is the logarithmic function, that constant is negligible. Yeah. So that is the time complexity analysis of selection structure. Then the third one is what I think is more interesting, is about the recursive function. I think this week tutorial you also have when we do the binary tree. Yeah, we trying to have an algorithm which is recursive one, which you want to in order, pre-order, post-order, traversal. All this you will find that their implementation are in recursive. And what is the time complexity of such recursive function is what we are interested to know. So same thing, is still count the number of primitive operation in such algorithm. But how do we analyze it? Then we need to know each recursive call. We use how many primitive operation, and then we did how many recursive call. So it's like the number of recursive call. Then if you know each recursive call take how many primitive operation, you sum it up, then that is the time complexity of that algorithm. So give you a simple example, same as the previous one. Instead of write it in the iterative way, I trying to calculate the factorial in recursive approach. In this case, you will find that I trying to, yeah, if it's the base case n equal to 1, then you just return 1. If n greater than 1, then you just recursively call the same function again and again by reduce the problem size by 1 in each recursive call. So in each recursive call, you basically only do a very simple thing. You just do one multiplication, and then you do a function call, then you just pass to the next recursive call. Then so let's say I only considered this multiplication. I only did one multiplication. So you take, let's say, this particular operation, it take C1. Yes, you will find that later you will find that actually they are more or less is the same. But this is a simple example. So we try to use a simple example to illustrate the things. You will find that the result definitely not surprising. You definitely expect that this particular one will be same as the previous one. Then you did how many recursive call? In this example, you did n-1 plus itself, total n function call. But recursive call you did n-1 plus itself, the first one. So each of them you only do some operation in constant time C1, maybe multiplication, n-1, whatever. Anyway, it's just a constant time in each. They are equal. Each time you repeat this procedure, except the last one. Last one, you just simply the last n equal to 1. That case, you return 1. Maybe that one take some constant time. Again, it's also a constant time. Maybe you can set C0. Yeah, you can, okay, I call it C2. Yeah, the last one is you take C2. The rest is all multiplication n-1. Then you recursive call. The last one is return 1. So overall is you did n-1, which is take C1 operation, and plus the last one is C2. But anyway, in the end, you find that this is a linear function. It's a linear function. It's a function of n. So it is a linear function. Not surprising, like what your friend said. Yeah, the time complexity is exactly same as the previous one, the previous iterative approach. But the recursive one, I think in the Monday lecture I've mentioned, actually this one, every time you recursive call, actually that will cost you more memory compared to the previous one, because every time you do the recursive function call, the computer is required to store all the status in the current call, because later you need to return back to the same position and carry on the process. Like this one, when you call this particular step, they actually need to run the recursive function call before they do the multiplication. So they need to do the recursive call, then they need to hold the status of n. And when multiplication something unknown, they wait for the thing return. So they need to hold the status. When they hold the status, actually they need to use a lot of stack memory to store all this information. But iterative one is already, you already optimize it. You only store just good enough variable for you to run each iteration. So, but this one, they need to store everything. They don't care. When you do the function call, recursive call, they have to store, you declare 10 variable in this function, they have to store all the variable or all the intermediate result. They need to hold it at that particular moment and wait for your this return function, wait for this particular function call return, and then they can carry on. So that one, you expect that they will use more memory in practice. But anyway, when we talk about time complexity, generally speaking, this particular one is a linear function. It's still a linear function. It's still a linear function in the time complexity. In the time complexity. Space, you expect it maybe use a little bit more. But in this example, I would say, yeah, if we talk about space complexity, it's still is about the same. I think you only store the n. Yeah, you just need the n. It's still the linear. It's still a constant. It's still one variable only. So maybe you declare you need to use 2 variable, 3 variable. It's still a constant. It's still a constant number. Yeah, it's not based on your problem size increase. You don't have to use exponentially increase the number of variable or memory storage. It's still proportional. It's still a constant time. You didn't increase anything. Your problem size increase. You still only have 1 variable to store, or 2 variable or 3 variable. Is still constant. So space complexity overall, when we talk about space complexity, this one no big changes. But if you really compare iterative approach and recursive approach, you can expect that recursive approach will use a little bit more memory. For in this example, okay. Another example, I try to count the number. In this one, I just want, instead of count all the primitive operation, I just want to know I just want to know you did how many compare the number with equal, whether equal to a this particular. I just want to count the number of this particular operation. Let's say I just want to know you did here, you did once, here you did once. Yeah, so in this one, it's just like trying to count the number. Yeah, count the number of A appear in an array. Count the number of A appear in this particular given array. So I just need to count in each recursive call. In this particular example, in each recursive call, you only did one, this comparison. You compare whether the index 0 is equal to A or not. You only did once. Either you enter this one or here. When you check this one, if your n is not equal to 1, then you will execute this comparison. So in each recursive function call, you only did one comparison. For this particular one, you only did one. You wouldn't run both of them. You won't be able to run both of them. Because when you enter this particular if statement, you definitely will return 1 or 0. You have no chance to carry on. When you enter this part, then you won't be able to, you don't need to run the earlier one. Then that means each recursive call, you only do one. You only do one comparison. You only compare the array 0 equal to A only once in each recursive call. Then now the next question is like, you did how many recursive call? So in this example, you can see that if it's equal to A, you will be run this line. Else you will run this line. Then your problem size n will reduce by 1 in each recursive call, which implied that you will run n minus 1 recursive call. Every time you reduce by 1, reduce by 1, reduce by 1, reduce by 1. So total number of recursive call is n minus 1 plus yourself plus the first call. So total is n call. But I asked, my question is that the number of recursive call. The number of recursive call is n minus 1. The first one is called by the main function, so not considered as a recursive call. But anyway, the process are exactly the same. They just do one comparison. So if only one, if your n is equal to 1, then you only do one comparison. Very obvious. Then you will find that when you have n, how about n? Then which means that you yourself, you did one comparison plus the n minus 1, the number of comparison you did in n minus 1. So that is the total number you execute in the problem size n. Agree? So such a equation, this equation is called recurrent equation. So once you come out this recurrent equation, and you also know the base case, which is when n equal to 1. When n equal to 1, you only did one operation. So in this very simple example, not surprising, you just solve this recursive function. You also already expected the answer, which is like, but I still go through it. That means what is the Wn minus 1? When your problem size is n minus 1, which means that the number of operation you need to execute is 1 plus the number of operation you did in n minus 2. So you repeat the procedure again and again and again and again. So it's 1 plus 1 plus 1 plus 1 plus 1 plus 1 to the last one. Eventually your n, the problem size getting smaller and smaller and smaller, and then 3, 2, 1. The last one definitely is the W1. The W1, you just simply substitute the base case, which is, you know, that is equal to 1. Then you just sum it up. Since this one you did n times, that's when you got n minus 1 times. So total is n minus 1 plus the last one. So total is n. So that is the time complexity of this particular algorithm. So this method, this approach, the key is I want to say is about this approach. This approach is a kind of a backward substitution. So in short, you need to know, identify the base case, and then you need to know the recurrent equation. For this one, is known as the recurrent equation. Recurrent equation, yeah. So is n equal to 1 plus the w of n minus 1. Yeah, if you tell me the number, if you're able to solve the wn minus 1, you just simply plus 1. Then that is the answer for wn. Then I just need to use the backward substitution. I will be able to backward. Yeah, once I know the W1, I know that what is the answer of W2. Once I know the W2, then I know that the answer of W3, W4, W5. Eventually, I will find out what is the answer of Wn minus 1. And from the Wn minus 1, I will be able to find out what is the answer of Wn. So that is kind of a method of backward substitution. So we need to use this kind of a trick to solve the time complexity of a recursive function. That one I will answer you later about the do we need to really calculate? Yeah. So another example, here we want to find the number of multiplication operation. So okay, this is what you learned in this week tutorial and the last week lecture, I guess. It's a pre-order traversal of a binary tree. If you have a pre-order binary tree, then they ask you did how many multiplication. You can expect that is the number of nodes you have. So how do you, let's say you don't know, just simply analyze it from the algorithm directly. Then in this case, you expect that you did, in each recursive call, you have done one multiplication. Yeah, you did one multiplication operation in each recursive call. But you in one recursive, in a function, you did two recursive call. So you did two recursive call. So which means that I need to, from here, I need to write down the recurrent equation first. From the recurrent equation is, which is, if I have, what did I do? If I have n, okay, I base case first. If my n is equal to 0, that means the tree is empty tree. In such a case, then I won't be able to enter. It's a null pointer. The tree is a null. Then the tree is a null, then I won't be able to enter this particular if statement. Then that means I won't do any multiplication. So the answer is 0. When the tree is only have one node, then I only did one operation. I only did one multiplication. Then the next two recursive call just do nothing. So once you know the base case, the next step is the recurrent equation. Yeah, before I come out. Okay, so the next one, W1, W2, if I have two level, that means this one is this way. When I have this one, that means the answer is, itself is do one multiplication, then I call this function the left subtree and the right subtree. So left subtree, yeah, is somehow W1. Then right subtree is W1. So total, not surprising, you do the substitution, is 1 plus 1 plus 1, which is 3. How about when you have 3 level? This one, which means that to solve this one, you can think that is 1 plus W2. This is one W2. This is another W2. So W3 is equal to 1 plus W2 plus W2. So very soon you can derive that the WK is equal to 1 plus 2 WK minus 1. So that is the recurrent equation. So you can carry on. Okay, this one of course is 7. Then so wk minus 1 is 1 plus 2k minus 2. Wk, so if you substitute all these things, you can observe that actually is 1 plus 2 plus 4 plus 8. So this one will be find that is 1 plus 2 plus 4 plus 8 plus 16 and so on and so forth to 2 power to k minus 1. So this is a geometric series. So I believe that you all have learned this before. So you should know that the geometric series formula, or if you can't, you can, here I show you how to derive it. If you can't remember, at least you should know how to derive it. You can derive it by your own. So if you have a series is 1 plus 2 plus 4 plus 8, then you just simply times the factor of the series, which is 2. Every time you, 2 times 2, 4, 4 times 2, 8, 8 times 2, 16, and so on and so forth. So R is 2. So then you just subtract the first equation with the second equation, then it's 1, the left hand side is 1 minus R, then the right hand side only left the first component and the last component here. So it's A minus A times R power to N. So that is the geometric series formula. Okay, anyway, this one, that means that I just substitute this equation, I can find out the answer is 2 power to k minus 1. K is the level of your binary tree. So expected, is a 2 power to k. The time complexity. So you have more level, that means that the number of nodes will grow in power of 2. So that is the recursive function. And you also can observe that when you have a recursive function and you call this recursive function, actually you call 2 times. The earlier is only do 1 recursive call. When you each function the function you have is only 1 recursive call. Normally is in linear. When you have 2 recursive call, you will find that the thing will grow very scary number, which is in power of 2. And this kind of approach, actually by right, I also need to prove, if I want to prove, if I use the forward substitution from 0 to 1, 2, 3, 4, then through the observation, I found that the increase is like in a geometric series. Actually, I need to prove it. Here I skip the proof. So I just based on observation find out that it's a geometric series. Then this kind of approach is known as method of forward substitution. I forward from 0 and then 1, 2, 3, 4, 5, 6. But you also can use the backward substitution to derive it. Which is from the backward means that I let the k, I know that the function, I did 1 multiplication and then I did 2 recursive call, and then I reduce the problem. By 1 level. And then I did this thing 2 times. So after you know this recurrent equation, you know your base case is n equal to 0. At k equal to 0, 0 level, you don't need to, it's an empty tree. You don't need to do any operation. You also can use the backward substitution to prove, to find out this particular one is 2 times. This wk minus 1 is 1 plus 2 k 2 w k minus 2, and so on and so forth. Eventually you also find it is a geometric series. Then it's 2 power to k minus 1. Okay, so that is the time complexity. Okay, now I will say this, I only count the number of operation, and you will find that actually each operation is not the key. The key is you did how many total number of operation you need to execute in an algorithm, and that will related to your problem size. If your problem size grow 10 times, then this operation, for example in this one, you will be from is a 2 power to k. So if you increase the level of your tree 10 times, then the number of nodes will grow in 2 power to k. It's quite scary. And a lot of this kind of operation in recursive function, you will find that it's a series. You will end up it's a series because every recursive call you may need to do different number. Can be 1 plus, can be earlier one is 1 plus 1 plus 1. Then this one is 1 plus 2 plus 4 plus 8. Depend, the number of operation will increase exponentially. So you expect that to solve all this kind of complexity, you need to use a lot of series. Can be geometric series, can be arithmetic series. Later you will find that we even can use the mix of the geometric and arithmetic. This is the arithmetical geometric series. Or more complicated can be go to this one. Is a power k power, yeah, it's a summation. That means this is 1 square plus 2 square plus 3 square plus 4 square. The series can be in this kind of a form, and so on and so forth. So that this is the formula. This is the power of 3 1 square cubic power of 3 3 power to 3, and so on and so forth. Yeah, you'll find that when you analyze the time complexity of recursive function, yeah, you may end up, you get this series. You need to know how to solve this series to find out what is the exact time complexity of this algorithm. So an example, for example, you have this nested loop, and in this nested loop, the outer one is I equal to 1 to n, from 1 to n. Then the inner, this nested loop is based on the I. Then I run I square iteration. So not surprising that the outer one will assign I to the inner one. Then inner 2 loop, nested loop, take I square. In other words, I need to find the total number of operation I need to take is 1 square plus 2 square plus 3 square plus n square. Then what is the total number of operation I need to take for this particular example, which is this formula. So you'll find that when you analyze a lot of algorithm, you always end up is a series, because it may not be every iteration you did exactly the same. Earlier example is simple. Every iteration, every recursive call, I did exactly 1 in each recursive call, in each iteration. So end up is a very simple series. It's just 1 plus 1 plus 1 plus 1. When you find that your every iteration you may run different number of operation, then you will become a series. But there's a pattern. Normally, definitely there's a pattern. Maybe it's increase in this way, 1 square plus 2 square plus 3 square. Then you need to know the series, the summation of this particular series. Then you will find out what is the exact time complexity. In this example, you will find that, not surprising, yeah, is n times n times n. So this one, the time complexity is n cubed. It's a function of n cubed. Okay? So why this thing we need to know? You can see if my problem side I trying to do n 100 to 10 power to 4, 10 power to 6. In such a case, let's say you got a few algorithms. The first one is 13, is a linear function. The second one is the linear logarithmic. It's linear n times log 2n, let's say. Then this one is n square. This one also n square with some constant. This one is n square plus 100. This one 2 power to n. You just compare different number of problem sites from n to what? From 10 to 100 to 1,000? No, 10,000. 1, 2, 3, 4. Yeah. Then million. How does it look like? The first one, let's say each operation I take 1 microsecond. 1 microsecond. Each operation, let's say I take 1 microsecond. Then if it's linear, 13n. Yeah, so you will see that this thing will grow linearly. And yeah, if it's 10, still okay. Yeah, for all these 6 algorithms, they take probably less than 1 second to complete, no issue. But when you go to this logarithmic one, you will start find that there's some problem. When your problem size is power to 6, 10 power to 6, you already need to take 259 seconds, nearly 5 minutes. And then when you go to n square, you go and calculate, it takes days to complete. This one also about in days, no, 3 years, near, yeah, 365. This one take nearly 6 months. This one take a few years. This one also takes 6 months. Because actually after that, that's why just now earlier I said the constant is not important. When your problem size increase to such a large number, behind got plus 100 is negligible one. Yeah, the scary one is the last one. Basically, I don't know how big it is. You have no chance to see the answer. Yeah, this one is already just 100. It already take you forever. Your computer spoiled, it still haven't come out the answer. So that's why you find that when we analyze the time complexity, we only concern is the order of growth. We only concern the order of growth. We're not so concerned about this factor and this constant number behind. Yeah, you can see from the diagram that if this is the problem size, I increase 10 times, 10 times, 10 times, 10 times, and let's say this is the operation, the times I take. So if your problem is linear, okay, then this is the 13n1. If it's a logarithmic, I mentioned I like this kind of logarithmic algorithm because it's much more faster than the linear one. Linear one is very, very slow as your problem size increase. When you go to linear logarithmic, then this one even slower. When you go to quadratic one, 13n square plus 100 or whatever. Starting there's some difference between plus 100. When your problem size small, that plus 100 there's some impact. But as the time grow, yeah, it's negligible. Plus 100 is negligible, no big difference. Then if you compare 13n square and 100n square, although of course 130n square is slower, but the growth is about the same. Their growth is about the same. Just this one is always slower, 10 times slower. 10 times slower. It's always 10 times slower. But the scary one is like is a 2 power to n or n factorial. If your computational time is n factorial or 2 power to n, you just increase your n a little bit, the computational times is already exponentially grow in a very scary number. So overall, you will find that n factorial is the faster growth. It's the slowest one. The growth, the computational time grow, the total time you take is the faster one. Initially, you find that it's very slow. Yeah, when your n is equal to 2, 3, 4, 5. But after that, after 10 factorial, 20, your problem size go to 10, 20, 100. The number 100 factorial is a very, very huge number. Yeah, same thing for 2 power to n. When your n is 2, 3, 4, not a big issue. But when your n is equal to 100, n equal to 1000, yeah, you will take a lot of time. It's very, yeah, your computational times is very large and very slow. Yeah, then linear one is okay. Logarithmic one, of course, constant is the best. Then logarithmic is the second lowest one after the constant, generally speaking. Yeah, so you will find that the 10 power to square, yeah, this 100, basically whatever constant behind can be negligible. You only always look at the highest order growth. If you have an algorithm is n cube, behind this n square or plus whatever linear 10 and yeah, actually this one and this one compared to n cube is nothing. As your n grow to a very large number. So normally we concern is the order of growth of the highest order of one. Yeah. Then 13n square and 130n square actually is always 10 times different. So that difference is okay one. That means I just need to this one is I just, if I want to scale, I just simply increase my resource 10 times, fixed. Then I don't need to worry that the problem size increase will affect the performance. So overall, you will find that we concern about the order of growth, not the exact, like what just now someone asked, the exact number of operation or each operation, the computational times, like just now I mentioned C1, C0, C, all these things is the computational times for each operation is not what we concern. We concern is about the order of growth with respect to the problem size. So my problem size, if it's the order of growth is n squared, then that is what we concern. If it's n cubed, yeah, that is what we concern. But behind you plus some additional, you need to declare a few variable at the beginning. You need to do some initialization. All this one-time operation is negligible compared to you have a nested while loop, or you have a very complicated recursive function inside a while loop. That computational time is far affect the performance compared to that all those constant times operation you did once or did constant number of times. So people want to represent the time complexity. They don't have to count exact number of operation they take, or they don't need to know exact number of times they execute one operation. They don't need to know. They only concerned about the order of growth. That's why they come out this asymptotic notation. Here we introduce three asymptotic notation: big O, big omega, and big theta. Yeah, basically these are based on the definition, is the set of function which have the same order of growth. So it's a set of function for big O notation is a set of function. That means there are a lot of function that grow at lower or same rate as G. Let's set example, if G is a linear function, whether I can switch to another mode. Here. Okay. So let's say I have an order of growth of let's say my gx is a linear function. My gn, okay, maybe I use the n. My gn is n squared. Then anything is the f, if I said f is in the OGN, which means that all these functions can be considered as f. F can be a linear function. F can, because based on the definition, is the set of function that grow at lower or same rate. So n is lower. Or I also can set fn is equal to 10n squared. This one is the same. The growth rate is the same. 10n squared or n squared, their order of growth are the same. So that's what it means. Or another one is 10n squared plus n. This one's still the same. The order of growth are the same. So that is the big O n. Maybe I have to stop here. Maybe I quickly go through the big omega. Big omega is the set of function. It's a set of function, not just one function. It's all the function. All the possible function are under this category, under this big omega. So big omega means that the order of the function that grow, the order of growth at higher or same. Higher means that they are all higher. That means n cube. Order of growth are higher. That means the function can be n cube, can be 2 power to n, can be anything. 2 exponential n also can anything. Is the higher than the G, higher or same rate. Of course, if it's a if Gn is n squared, then anything is a quadratic function, then that is considered same rate. Then if I use the big theta notation, the big theta notation is represent those are at the same rate. Then it must be quadratic function. In this particular example, it must be a quadratic function. That means those are 10 power to 10n square or 11n square plus 7n plus 5. Yeah, all these are under big. That's if you have a function fn is equal to this, fn is equal to this. In this function, I can set that this n is belong to big theta g because they have the same growth rate. Of course, they also, based on the definition, also you can set this a big omega, also it's a big O. They are the same. But more precise definition, more precise one should be big theta. Because all these are quadratic function. Okay, maybe next week, next Monday, I will talk more about the exact notation, the definition in the next Monday lecture. In that case, I think I may need to postpone the tutorial to week 9. Yeah, to be fair to those people who have the tutorial class on Monday. Yeah, so I would like you to have a time to understand it. Let me answer some question. During the quiz, are we required to calculate the exact result? So as I said, you will find that when we talk about time complexity, one of the important things we're talking about the order of growth. We are not talking about the exact number of operation or the compilation time. So after this point onward, the slide you'll find that I no longer mention about the constant C1, C2. I don't need to really set that each operation takes C1, C2, C0. Earlier slide I show you is just let you know that each operation takes some times to operate, but I'm not so concerned how much time you take. I concern is you need to run this particular operation how many times you run this particular operation. You have a for loop, you need to run n times. I concern is you run n times of this particular operation. Yeah. So you can see that after that we don't have to concern about all this constant number of operation, constant number. We only concern is the order of growth. So you only need to represent in this asymptotic notation. Yeah, your time complexity, you will represent it in asymptotic notation. You just need to represent the order of growth. It may not be big O. So it's like, how do you choose the big omega, big theta, and big O? I will discuss on Monday, next Monday lecture. Okay? Any other question? If not, I will end today's lecture. And next, maybe quickly go through this. Next week, next Monday, I will talk about big O notation, okay, and big theta notation, and give you one example which you have learned, the sequential search. Okay, I will talk about the sequential search, the time complexity of sequential search, which you have learned it when we cover the linked list. Actually, all the linked list actually is a kind of a sequential search because you have to search read every nodes in the linked list to get the answer you want. And some simplification of the asymptotic analysis, I will talk about it, and I will talk about different class. And yeah, the space complexity, once you know the time complexity, space complexity is just calculate the number of memory units, so that is not that critical. It's not that difficult to analyze compared to time complexity. If you know how to do the time complexity, the space complexity, simply look at the variable, the array you create, you declare, then you just can easily find out the number of memory unit you need to use for that particular algorithm. Okay, so this thing I will discuss on Monday lecture. If time allow, I will talk about hash table on Monday. If not, I will talk about hash table on Wednesday. So once I cover the hash table, I will start release the assignment. Yeah. So if no other question, I will end this particular lecture streaming. Thank you.